Today we are going to discuss moving coil galvanometer, its principle, its working, its construction, and the details of it. Also we'll discuss how we can convert a galvanometer into an ammeter, how we can convert galvanometer into voltmeter. So all these discussions will be done today. Moving coil galvanometer is a device which can detect current in a circuit, and it works on the principle that a current carrying loop suspended in a region of magnetic field experiences a torque which is proportional to the current flowing through it. Now let's discuss construction of moving coil galvanometer. In moving coil galvanometer, we have a coil C of several turns which is wound over a soft iron piece I, and this is suspended by means of a phosphor bronze wire from a torsional head H, and this T represents the phosphor bronze wire through which this coil is suspended in the region of magnetic field produced by N and S, which are representing concave shaped pole pieces of magnet. These are concave shaped pole pieces which is used to produce radial magnetic field in the region of which this coil will be turning. And from the lower part of this coil, there is a spring S dash which is attached. This spring is made of again phosphor bronze, and at the base of it we have the leveling screws provided as L1 and L2. L1 and L2 we are using it to level its base so that we put it on a proper horizontal platform. Let's now take its theory. Suppose N is capital N we are using to represent number of turns of this coil having area A and carrying current I. This is suspended in a region of magnetic field B. So B represents magnetic field strength in the region of which this coil is suspended. So if it is such, then the torque experienced by the coil, this will be equals to NIAB sine pi by 2. Now why it is pi by 2? Because we have taken radial magnetic field which is produced by these concave shaped pole pieces of magnet, so that vector area will always be perpendicular to the direction of magnetic field. So in this case it will be NIAB. This is the torque experienced by the coil. Now suppose we assume that C is restoring couple per unit twist of this spring S dash, and theta is the angle through which this coil is turned. So restoring torque, this will be equals to C into theta. Suppose I represent restoring torque by tau dash. So in equilibrium, when the coil will finally settle, then we have tau equals to tau dash. This is there in equilibrium. So in equilibrium we'll find tau is equals to tau dash. So we have NIAB, this is equals to C theta, or I is equals to C by NAB into theta. Now here, this term C by NAB, this is a constant. Now, why? Because the restoring couple per unit twist of this spring will have a fixed value. N, which is the number of turns of the coil of the galvanometer. So for a given galvanometer, this is also fixed. A, which is the area of the coil, so that is also fixed. For a particular strength of the magnetic field in the galvanometer, this B is also fixed. So all these will indicate that this is a constant and this is your constant here. This is the constant. And this is also called as galvanometer constant. This is your K, and that is your C by NAB. Now again, let's just see how we are taking its working there. When we pass electric current, in that case, the coil will experience a torque, because the torque is given as NIAB sine theta. So as the current is passed through the coil, it will experience torque. So what will happen? The coil will turn. If the coil turns, the spring which is attached here from the lower part of the coil, that one will get twisted. And if it gets twisted, in that case, there will be restoring torque developed in that, which will try to bring that one to its original position or original orientation. So it will develop a restoring torque on this coil also, because it is attached with this coil. So it will try to turn the coil in just opposite direction to the direction which is produced by the torque due to the current which is passing through this coil. And remember that this restoring torque is C into theta. So as the coil will turn, theta will increase, because for a particular value of torque, it has particular value of current, there is a particular value of the torque there. So due to which it will turn. As theta increases, then restoring torque will also increase. So a time will come when the two will become equal, because for a given value or for a particular value of theta, it is possible that C into theta will acquire the same magnitude as the torque, that is NIAB, produced in the coil. So that will be the state of the equilibrium there for that coil. And this is exactly what happens in equilibrium. So in equilibrium, the coil will be in a rest condition there, or it will settle there. So we can get this condition there. And here you can see that current is proportional to theta. So this current, as it is proportional to theta, it can be used to measure current flowing through the circuit. Now, for the measurement of the current, there are different ways there. Here, there is a small mirror attached to the wire. So if a small mirror is attached to the wire, and in actual case what we do, we put a light source in front of it. So light falls on the mirror, it gets reflected. There is a scale there. On that scale, it will fall. So if the coil turns, the mirror will also turn. As a result, what will happen? As the mirror is turning, the reflected spot of the light will take different position from its equilibrium position. So it will shift to some other position on the scale. We will measure how much distance it has moved. And then we can find out at what angle it has turned. Because we can find out what is the shift there in its position, what is the distance of the scale from the mirror. That will help us to measure the angle through which it is shifted. Advantage of the mirror is that it is a small light mirror attached there. So, and also, so it is not going to change the mass of the coil much there. Another thing is that if the mirror turns through theta, the reflected ray turns through 2 theta. So we will be able to measure the angle through which this coil is turned more accurately, because the shift will be large. So we can measure that one more accurately here. Other way may be that we can attach a pointer with the coil of the galvanometer and the pointer will turn. So in that case, the deflection of the pointer will indicate the angle through which the coil is turned, which in turn will be depending upon what is the angle. Deflection of the pointer of the galvanometer will be proportional to the torque which is produced there and the equilibrium state which has been acquired, and the torque there will be depending upon the current which is passed through it. So we can measure current there. So this is the working of the moving coil galvanometer and its theory. There is a term used for the galvanometer, that is the current sensitivity. It is the deflection produced per unit current passing through it. So it will be theta by I. That is the current sensitivity. And we have just seen that I is C by NAB into theta. So we can get the value of theta by I as NAB by C. So this is the current sensitivity. So if you want higher value of current sensitivity, then N should be large, A should be large, and B should be large. So for high current sensitivity, NAB should be large and C should be small. Now for high current sensitivity, definitely NAB should be large. But there is a limit up to which we can make NAB large. Because if you are increasing N, that means you are increasing number of turns. If you are increasing the number of turns, then the coil will become heavy. And if the coil becomes heavy, in that case, it will not be very sensitive for measuring a small current there. Because a small current will not be turning it to a large extent there. So there is a limit up to which we can make N large. Again, A, which is the area of the coil there. So their area also we cannot make large, because if it is large, in that case the size of that apparatus or the galvanometer will become large. So if the area of the coil is large, in that case magnetic field may not remain uniform through it, because we have used soft iron piece inside the coil just to concentrate the magnetic lines of force passing through it. If the coil is having large area, in that case there will be a magnetic field not throughout uniform through that particular coil. Then is your B. B we can make large. If you are using strong magnets, there will be the heavy magnets there, and if it is heavy magnet, the galvanometer will not be easily transportable. So definitely NAB should be large for high current sensitivity, but there is a limit up to which we can make them large. Another factor which is there, that is C, which is the restoring couple per unit twist. We can make this one small, then current sensitivity will be high. So we search for the material which has a small value of C. Phosphor bronze is one such material which has a small value of C. That is why phosphor bronze coil is used in this moving coil galvanometer there. Because it will have a small value of C, it will give large value of current sensitivity. Also, this does not get oxidized easily, and its conductivity is also large there. So in that case, it is most suitable for using in moving coil galvanometer. Another term is voltage sensitivity. It is the deflection produced per unit potential difference applied across the galvanometer. So voltage sensitivity will be theta by V, which we can also write as theta by I into R. And theta by I, just we have derived earlier for current sensitivity. This is NAB by C. So it is NAB by C into R as voltage sensitivity. Again, if you want high voltage sensitivity, then NAB should be large. and C and R should be small. So then we can get high value of voltage sensitivity of the galvanometer. Let's now discuss conversion of galvanometer to ammeter and voltmeter. First of all, let's take conversion of galvanometer into an ammeter. A galvanometer can be converted into an ammeter by connecting a low resistance shunt in parallel with the galvanometer. An ammeter is always connected in series with the circuit. Suppose G is the galvanometer. G also we are taking as the resistance of the galvanometer there, and we want to convert it into an ammeter. So we have connected a shunt S in parallel with this. Suppose the current I is flowing through the circuit. In that case, it will get divided into two parts there, through the galvanometer as well as through shunt. If Ig represents the maximum current which can pass through galvanometer, so this is your Ig, so current will be I minus Ig through the shunt. And here this together is called ammeter. This is your ammeter. So here, if you consider potential difference across it, so it will be Ig into G. This is also equal to I minus Ig into S. So we can get the value of S as Ig into G divided by I minus Ig. This is the expression for the shunt which is required for converting the galvanometer into an ammeter of particular range. So this is the value of the shunt resistance. And if you consider the resistance of ammeter, so now you can see as it is parallel combination of G and S. So in this case, it will be G into S by G plus S. So what we have got here, that in order to convert a galvanometer into an ammeter, a low resistance shunt is connected in parallel with the galvanometer. So here we connect low resistance shunt in parallel with the galvanometer to convert it into an ammeter. And second point, ammeter is always connected in series with the circuit. So this is the conversion of galvanometer to ammeter and the value of the ammeter which is finally produced. Now, why we are using shunt resistance, why we want to convert it to an ammeter of different values there. Suppose we have a galvanometer, it has a particular range. So that means we can use it to measure current up to that particular range. Suppose it is 1 ampere. That is the maximum current which the galvanometer can measure there. And I want to use it in a circuit where the current is 2 ampere. So we cannot use that one. Or suppose there is a circuit where the requirement is of the current in that circuit is 5 ampere. And we want to measure current in that. So for that, we want ammeter to be used. But that galvanometer we cannot directly use because maximum current will be 1 ampere there. So we convert that one into an ammeter so that it can measure current up to required range. And how it can be done? If you bypass the current or maximum current through the shunt. So there are two things. First of all, we have a circuit This is suppose a circuit whose potential difference is 12 volt, and there it is a 3 ohm resistance connected there in the circuit. So what is the current there? It is 12 by 3, that is 4 ampere. In order to measure this current, we connect an ammeter there or galvanometer there. So suppose we connect an ammeter in series with the circuit. This ammeter will also have some resistance. Suppose its resistance is 1 ohm. So in this case, the current which is measured will be now 12 by 3 plus 1, that is 4, or it is your 3 ampere. That means the actual current in the circuit was 4 ampere. But the moment we have connected ammeter to measure it, the current has reduced to 3 ampere. Obviously, the measured current will be not the same current which was actually flowing in the circuit. So the reading there will be not for the correct value of the current. If you want the current measured by the ammeter to be as close as possible to the true value, then the resistance of this one should be very small. It should have low resistance. First point. Second is that if I have suppose the galvanometer and it can measure current up to 1 ampere. If I connect a resistance of same value as that of the galvanometer. So if it has a resistance connected in parallel with the galvanometer having same value as its own resistance, so now the current will get divided. It will get divided into 2 equal parts. So this time, if I send current of 1 ampere, it is 0.5 and 0.5. Or if the current in the circuit is 2 ampere, it will be 1 ampere through the galvanometer, 1 ampere through shunt. If the galvanometer was there, which can measure current up to 1 ampere, I can easily use it in the circuit where the current in the circuit is 2 ampere, because the current through the galvanometer is actually 1 ampere which is flowing. So we can increase its range. At the same time, just by connecting a resistance of same value as that of the galvanometer resistance, now the equivalent resistance of this entire one will be 0.5 ohm only, because it will be the parallel combination of 2 1 ohm resistances there. Suppose if I assume that this is also having 1 ohm resistance, this is also having 1 ohm resistance. So the resistance which was 1 ohm initially, now it has become equal to 0.5 ohm. So that means the resistance of the ammeter which is produced will have low resistance, which is the requirement for measurement of the true value of the current or more accurate value of the current in the circuit. What we actually do, we connect a very low resistance shunt in parallel. Like suppose if it is 5 ampere to be measured, in that case we'll send current so that 1 ampere goes here, 4 ampere here. So it is your 1 ampere and it is 4 ampere. So that means the resistance should be in the ratio of 4:1. 4 ohm should be resistance of this and 1 ohm should be of this. That means basically 4:1 ratio should be there. The resistance of the shunt is small as compared to this. And if I am using 4 ohm and 1 ohm resistances in parallel, so now the equivalent resistance will be how much? It will be 4 by 5. That means 0.8 ohm. Remember, the resistance of the galvanometer was only 4 ohm earlier, but the ammeter which you have made, now it will have resistance of 0.8 ohm. It is much less than that. So the reading shown by this ammeter will be more accurate than the reading shown by the galvanometer, which is being used there as an ammeter. Second thing, that now the range has also increased. Earlier you were able to measure the current only up to 1 ampere. Now we can measure current up to 5 ampere. One more thing is there. The reading shown in the galvanometer will be proportional to the current flowing through it. So the current which will flow through is of say 1 ampere or up to 1 ampere. But the actual current is different. Say it is 5 ampere going there, 1 ampere will go through galvanometer and 4 ampere will go through the shunt. So in this case, if the deflection in the galvanometer is up to 1 ampere, will it measure the current flowing through the galvanometer or will it measure current through the circuit? We want to use this one as an ammeter. That means it should measure current flowing in the circuit, not through the galvanometer. So what is done? We change the calibration in the galvanometer, which is being used as an ammeter. So a scale will be changed. If earlier the scale was suppose 0 to 1, the calibration now it will be done from 0 to 5. That means if the galvanometer is having 1 ampere current, it will give you the maximum deflection there. And now as calibration have been changed, so now it will show calibration as 5 ampere there. So by changing the calibration there or making proper scale, we can use the ammeter to measure the actual current in the circuit. So this is the conversion of galvanometer to an ammeter, and why we are connecting shunt there in parallel to make it ammeter, and what is the advantage of that we all have discussed. Now let's see how we can convert a galvanometer into a voltmeter. For conversion of galvanometer to voltmeter, we connect a high resistance shunt in series with the galvanometer, and then a voltmeter is always connected in parallel with the circuit. So these two things we must remember. One, that a high resistance shunt is connected in series with the galvanometer. So if this is the shunt, this is the galvanometer, we have connected in series with this. This shunt should be of high value. And a voltmeter is always connected in parallel with the circuit. Why we are connecting voltmeter in parallel with the circuit? Because we want to measure potential difference between 2 points of the circuit. So for that, definitely it must be connected in parallel, then only you will be able to measure the potential difference of 2 points. Why ammeter is connected always in series with the circuit? Just because we want to measure what is the current flowing through the circuit. So unless the current measuring device is connected with the circuit, in series with the circuit, it cannot measure that. So that is why we connect ammeter in series and voltmeter in parallel. Again here, if you have the shunt of high resistance connected there, so when the current will flow there in the circuit I, it has now 2 paths to flow, one through the resistance across which you want to measure the potential difference, and other is the galvanometer. As it is high resistance in series with the galvanometer, so very low current will flow through this circuit. That means through the voltmeter. And maximum current will go through the circuit. If the maximum current will go through the circuit, in that case the measured value of the potential difference will be more close to the true value. Because again it will be the same thing if here we have the resistance R and we connect a voltmeter there in parallel. So if the current which is flowing through the circuit is I, here it is your I dash and this is suppose your I double dash. So potential difference which will be measured will be your I dash into R. So if this value of current is less in that than the current, in that case the measured value of the potential difference will be less than the true value. True value is how much? I into R. If this is not connected, in that case it is I into R. That is the true value of the potential difference. across this R. But as we are connecting a voltmeter, suppose the current now is I dash, so it will measure the potential difference as I dash into R. If you want this measured value of the potential difference to be as close as to the true value or actual value, then this I should be as close as possible to the true value. So for that, we connect the shunt in series with the galvanometer so that we can increase the resistance of the voltmeter. And as it is connected in parallel, very low current will flow through that voltmeter. So it can measure the current and the potential, it can measure potential difference more accurately. Now let's see what should be the value of the shunt resistance. So here, if I assume that G is the resistance of the galvanometer, S is the shunt resistance, R is the resistance across which we want to measure potential difference. And suppose the potential difference is V when the current was I through the circuit. This current will definitely get divided into two parts, Ig as the current through the galvanometer and I minus Ig will be the current through the resistance. So here, if I measure this potential difference V, this will be Ig into G plus S, or G plus S will be V by Ig, and that gives the shunt value as V by Ig minus G. So this gives the value of the shunt resistance which is required to be connected in series with the galvanometer to convert it into an voltmeter of suitable range or particular range. And now if you want to find what is the resistance of this voltmeter, because G in series with the shunt is the voltmeter. So the resistance of the voltmeter will be equal to series combination of G and S, so it is your G plus S. So this is the resistance of the voltmeter which is connected or which is being produced here. So G plus S will give you the resistance of the voltmeter hence formed. So this is the conversion of galvanometer into ammeter and into voltmeter. What should be the shunt resistance, how it should be connected, how the device should be connected, all these we have discussed in this discussion.